So ProteinMPNN is a model, it's a graph neural network, but it really builds upon John Ingraham's work in 2019, where John created this structured transformer is what I think people have dubbed the model, although I don't know if John agrees with that name. So it's a graph neural network in the sense that if you think about like AlphaFold, every residue talked to every other residue, right? We had the attention mechanism that allowed every residue to connect to each other and pass information back and forth. The graph neural network is structured a little differently. Rather than allowing every residue to talk to each other, it's actually restricted based on the local neighborhood of every residue. So based on maybe this beads on a string like protein, if we're interested in this residue in particular, it looks at its 10 nearest neighbors, something like that. In ProteinMPNN, 48 or 32, it kind of depends on the model. But it looks at its nearest neighbors and gets its structural information about its local environment. As we add more and more of these layers, you can think every residue is looking at its nearest neighbors, which means even the residue at the end of that nearest neighbor's residues is looking at its nearest neighbors. And so as you add more and more of these convolutional layers, is kind of the idea, you essentially get longer and longer range effects. So the model starts to look farther and farther away. It has an idea of what maybe the structure is on the other side of the protein, although it maybe have less of an effect than the very local structure. So as you can imagine, this may be particularly well suited for structural design, for sequence design, because you may expect that the sequence constraints are very local in nature, but of course there may be effects on the other side of the protein that do influence the current residue you're interested in. So John Ingraham's structure transformer had two main components. We had the structure encoder and the sequence decoder. The structure encoder took the backbone information and every residue talked to its nearest neighbors to kind of get an overall sense of what this protein looked like, maybe what's favorable, where the other residues are, et cetera. And then once we've had this encoded representation of the protein's backbone, we start to do autoregressive decoding. So John started from the N-terminus to the C-terminus, and he started assigning amino acid types based on what the model thinks would be best suited for here. And the way that it does it, let's look at somewhere in the middle. These guys look at its nearest neighbors like before, but now the residues that have already been decoded have some sort of sequence information there. And so now they tell this residue, hey, I am an isoleucine. Think about that, and how does that affect what you think you should be? But we also know on the other side of the protein, it may have neighbors that haven't been assigned yet. So it needs to keep into mind that we haven't assigned these residues yet, but they still need to be compatible with the overall structure. Yeah.
So for the like neighbors, is that in the structure or like sequentially?
That's a good point. So these are based on the structural coordinates. Okay. So the nearest neighbors based on C alpha distances. Of course, you could define it in different ways. You can maybe have a radius graph. So everything is considered a neighbor if it's within maybe 10 angstroms. But in this case, every residue has a fixed number of neighbors.
Is there a reason not to do the whole protein at once? Is it just computationally not needed?
Yeah, I mean, you can totally imagine throwing attention on this and letting every residue talk to each other. There have been many papers that do that. It is more efficient to do it like this. This is more scalable. Attention grows quadratically with the number of residues. This grows linearly. So you have those kind of benefits. It's also much faster. I don't know if we know what works better yet. The graph neural networks tend to be really efficient and work really well. So I think that's kind of where we're at right now.
What would be the drawback of doing like a one-shot prediction?
Yeah, that's a good question. So rather than maybe making a prediction based on the previous ones, you can make a prediction maybe all the sequence all at once. However, you may have because you're sampling those distributions independently, you may not really capture the correlation between the different residue positions, which really can influence what's coming downstream. So these residues are conditioning this guy's prediction. So it does provide extra context and extra information for its decision. So it provides a little bit more correlation and maybe better predictions.
But you could theoretically build a model that doesn't start from like the N-terminus, but start in the middle.
Yep.
And build it randomly, right?
That's actually what ProteinMPNN does.
Okay.
Yep, that's a very good point, very good insight. That's exactly where we're going. So as you can imagine, this may not be the best way to do it. And that's one of the changes that Eustace made when he created ProteinMPNN. But we'll talk about that in a few slides. All right, so this is kind of what the network architecture looks like itself. We have the protein structure, which is a graph. We have our nodes and edges. Our nodes are each individual residue. And it's connected to its nearest neighbors. And so that edge kind of represents the interaction between these two nodes, these two residues. Once we have these embeddings, which we kind of build from features like so it includes like the geometry of the backbone and stuff like that. Those are kind of the features that we're getting at this point. And this includes information between the two residues, like orientation and stuff like that. From here, we update the nodes by performing self-attention within the local neighborhood. So it is restricted still, but it's the attention operation. And then the nodes update themselves, ask themselves some questions, and update them based on that. And that encodes the entire protein backbone structure. Now, once we get to the decoder, we apply this causal self-attention, which is really just the way of saying that we look at the residues that have already been decoded, make our prediction based on that. The other residues are still masked. We don't know exactly what will be there. We don't know what they're going to be yet. So it's a way of like limiting the amount of information that this node sees. From here, it updates itself, and then from there, it makes a prediction of what amino acids it can be. We sample one and continue down the process. It is autoregressive. N terminus starts first, and then we continue all the way to the C terminus. Cool. Any questions on John's model?
You said that it was linear before, but you have self-attention there.
Yes, so this is self-attention, but restricted to the neighborhood of each residue. Okay, which is also interesting that the attention mechanism typically lends itself to the transformer name, but John actually found that the message passing neural network performed better than the transformer, which is weird because people call his model the structured transformer. I don't know, but this is the image in the figure from the paper, but the MPNN style architecture did perform better, and that's what Eustace used for ProteinMPNN. We'll talk about what MPNN stands for and means when we start talking about ProteinMPNN. Yeah?
So in general, what edges are present in the graph is determined by the distance, right, between the nodes.
So it's based on the nearest neighbors. So every residue is connected to its 32 nearest neighbors. It has an edge if they're connected.
Oh, okay, so there's no distance cut or something like that.
There's no distance cut off. So, right, so if you're on the surface of the protein, you still have 32 neighbors. But they're all maybe on this side of you rather than around you.
Is it also in the graph information? So in like edges, is it are the actual like edges the bonds between the neighboring proteins in sequence?
It's not necessarily bonds. For example, like when you there is.
Wondering if the two residues that are connected to the one that we're to the node are somehow preferred. So are the edges somehow prioritized, or are they treated exactly the same as all the 30 other proteins in the?
Yeah, that's an interesting question. When we're doing self-attention, the attention weights the different nodes differently, so it is kind of different. However, in the message passing style, which Eustace has used, every message coming from your neighbors is weighted equally. But the model still does know which residues are next to each other, because there is this embedding that gives it a local relative sequence position. So if we're at residue I, it'll know which residue I minus 1 is, and it'll know what residue I plus 1 is. So it knows relative to what you are, where everybody else is in sequence space. But it also knows where they are geometrically relationship in the 3D space as well. So the edge information both contains sequence space information and geometric 3D structure information. Yeah?
Does this change at all when you include a template or like a target? Or is it even considering that during the decoding step?
When you say template, are you referring to like another chain that may be fixed?
Yeah, let's say you're designing the binder sequence and you have a target set sequence.
Mm-hmm.
When it's choosing the 32 nodes, is just picking from the design, or is it also going to be picking from that target?
Yeah, so one thing I want to say is John's model was only trained on monomers. Hustis's model was trained on complexes, and it does talk to everybody. So it does consider like a target protein that is fixed. So if a residue is at the interface, some of its neighbors will be within that same protein, some of them will be in the other protein.
Is it all then, might be a silly question, is it all equally kind of weighted, or is it going to be caring more about, say, like the other residues in the other chain at the interface, as opposed to, say, the rest of the structure?
So the messages that come from everybody is still equally weighted, although the messages may like have different magnitudes depending on whatever information the model thinks is useful. Okay. So let's talk about actually ProteinMPNN now. Like I said, we have a backbone. We throw it through the model, get a sequence. A little bit about kind of how it performs before we start talking about the model. We compare it to Rosetta here. As you can see, the line for ProteinMPNN is shifted upwards, meaning that overall it is much better. However, there are some differences as we start looking at the centrality level of each residue. So as we start moving more from the center, Rosetta is pretty good at choosing residues in the core. That's primarily because it's super easy to do that. The geometry and the neighborhood around each residue in the core is very well defined. It must be really well packed. So it's much easier to select a residue in the core of a protein. However, as we start moving more and more towards the exterior of the protein, it may be a lot more variable what is acceptable here. There's a lot less structure, there's a lot more flexibility. It's also solvent exposed, which allows it a lot more options too. But interestingly, we see kind of in this intermediate region the biggest difference, as you can see by the dotted line, the dashed line, indicating the fraction.
What is fraction?
Oh, it's just this guy divided by this guy. Or you sum them and then you take this guy divided by it. Yeah. It's just kind of comparing those two lines.
Can you define what sequence recovery is?
Yeah, sequence recovery is sequence identity. Sorry. Yeah. Another thing ProteinMPNN did was added noise to its input coordinates. The idea there is that maybe the coordinates have some sort of information about what the sequence should be baked into them. And this can kind of come from some of the software people use when they're creating these crystal structures, when they're solving the crystal structures. They have preferences about the bond lengths and bond angles of each residue type. And so if you tell the model exactly what the coordinates are, it can really pick up on that and start to just memorize exactly what the software is telling this bond length should be between the N and C. So it can really start to pick up on that. One thing that Hustis did was started introducing different levels of noise to the coordinates. So literally, you take your coordinates, you sample a Gaussian with a mean of whatever, and you add that to the values of each individual coordinate. And interestingly, as you do this, the model starts to become more robust. It becomes more, it becomes better at designing sequences that can fold into that structure itself. So as we see here, we have sequence recovery on this axis. As we start adding more and more noise, it's harder and harder to pick up the true sequence signal, which is expected. You can see there's a huge drop off when we go from 0 to like a little bit above 0. And that really highlights the fact that the model is able to memorize what kind of sequence distance and information is really stored in that those structures. So a little bit of noise makes it more robust. We also see a dramatic improvement in the success rate of AlphaFold 2 predictions. And it actually kind of grows. So even as you add more and more noise to the coordinates, AlphaFold's liking these structures more and more, which is maybe surprising, but it's I think also really points to the fact that these models are really good at kind of memorizing the sequence associated with the structure. And by introducing noise, you're able to kind of, I don't know what the word is, you can kind of start imagining maybe you can be, you're less confident in what the overall structure is, so you can place your bets in, you're not placing all your eggs in one basket, I guess is what I'm trying to say. You're diversifying your sequences more, but also making them more flexible in the sense that more amino acid types can be allowed there. This will, of course, hurt the perplexity because you're making it harder for the model to actually choose, but it does improve the success rate with AlphaFold. So that's actually probably a more useful metric than maybe perplexity. Questions?
So I know that there are different model weights with different noise values. Practically speaking, how should we go about picking the level of noise?
That's a good question. I think we typically just use 0.1. I don't know. I don't really have a great reason why. I think that's the default that like Eustace uses and people use for like RF diffusion. So yeah, I don't know if you guys have any more insight into that, but.
Yeah, I tend to go up on that value if I find that it's giving me sequences with like a lot of alanines or something, but I usually stick to 0.1. Yeah, I go up to like 0.2 or 0.3 as a stick.
Yeah, there's another knob you can turn called the temperature value that increases diversity as well. But yeah, people do like to add a little bit of noise to their structures. 0.1, 0.2 is usually a good value for that. Okay, let's talk about the model itself. So I said that John Ingraham had this model that performed sequence encoding, structure encoding, and then sequence autoregressive decoding. Eustace started with that baseline model, which already has, it's a pretty small model, like 1.4 million parameters, which if you compare it to like AlphaFold has 98 million parameters. So it's like 100 times smaller. It's also got a PDB test accuracy of around 41%. This is sequence recovery metric. It also includes the perplexity, so it's choosing between 6.5 residues on average. And the AlphaFold accuracy, if you refold that structure, how much does it actually agree? How often does it agree? It's around 41%. And that agree metric's probably like ARMIS-D2. I don't remember exactly what they used here, but it's something like that.
For the PDB test, was it all the structures in the PDB database at that time, or?
It's a test set. So they have, it's their test set. So they have all the PDB structures. They split it into their training, validation, and test set. They held the test set away, did all the optimization on the model stuff, and then they evaluated it on the test set.
Oh, I guess, like, how did they choose what PDBs from the database to include in their?
Oh, it's,
like both the test set validation training.
yeah, so I think they just chose structures that have less than 40% sequence identity is the cutoff that they chose, and that's how they deduplicated the data. So anything greater than 40% sequence identity, they kind of threw it away, and then they split it randomly after that. Okay, so Eustace performed some experiments by changing some of the model. First, he added distances between all the individual atoms, and he included this in the edge features. So originally, the edge features were just an orientation. So if we imagine this residue and this residue, it's really just the rotation matrix and translation vector to put this residue on the other residue. By adding these, he provides more atomic detail about what the actual orientation and the geometry of the structure is. So maybe it's even a little bit more accurate because we're including not just the orientation between the C alphas, but we're also including C beta, C, N, and O. So it's just kind of more atomic detail that the model sees. This has a dramatic impact on the performance. We see a massive increase, about 8% in the test accuracy, which is recovery or identity. We also see a dramatic decrease in perplexity, which is good. It's now choosing between 5 residues. And we also see that it improves AlphaFold's, AlphaFold likes these sequences more, and they refold into the target backbone a little bit more often. The next thing that Eustace did was added updates to the edges. So originally in the model, only the nodes were being updated. So it would look at its neighbors, update its node information, and then it would look at its neighbors, update its own information, keep doing that a few times. With the edge update, each node would look at its neighbors, update its node, and then these two nodes would update their interaction between each other. And so this provides the model more flexibility. It's able to pass these messages back and forth a little easier. It also gives it allows it to be more complex and more expressive. And so this is actually an addition off of the baseline model, not off of experiment 1. And it adds a lot of parameters. A lot is relative, but it also improves the PDB accuracy by about 2%, decrease in perplexity, increase in AlphaFold accuracy. By combining these two, the experiments 1 and 2, even more improvements. We now jump over 50%, below 5, and above 46%. And then they implemented the random decoding. So like I said, John's model left to right, N to C. Now we're decoding in a random order that is determined uniquely, or is determined randomly at every inference. Whenever you give it a new protein, it randomly decides what that decoding order is. And that also provides a benefit. As you can imagine, looking at residues that are just decoded before it may not be super useful, but by randomly decoding it, you maybe have more information about what is around you, and so you can make a better decision. So this is the main overall figure for ProteinMPNN. Like I said, it was trained not just on protein monomers, but also protein complexes. As we can see here, we have 2 chains. Each residue is located at their C alpha, but looks at its nearest neighbors and computes all these distances between each atom in the backbone itself. This is that atomic detail of distances that really gets encoded in the edges itself. So that represents our edge information. The node information is actually a bunch of zeros. It's actually, there's no node information, but this gets changed really quickly once we start passing messages between each other. So we have our initial nodes and edges. The nodes get updated by passing messages between its nearest neighbors. The neighbors then update their edges between each other. This happens 3 times, and that's the encoded backbone of the structure. Now we go to the sequence decoder part. We still have the edges and the nodes. The edges are no longer changing now. So our nodes are going to be updated based on its nearest neighbors. The first residue that was chosen by the decoding order will make its prediction, get its probabilities, sample a sequence, and then the next node in the decoding order will look at its nearest neighbors, pass messages, update itself, make its probability prediction, and then its sequence. Eventually, the whole sequence will be filled in, but also this is a random order, so it's not necessarily N to C. And after you're done, you'll have that full protein sequence. Okay. This is just another way of highlighting that decoding order. So in the left or right, it uses the context that came before it. These amino acids are fixed, so it's decoding those, but just assigning the fixed residue type. But then this blue one makes its prediction based on the previous ones. And then in ProteinMPNN, it's based on everything around it. So this residue would be able to see these two. Because they're fixed, they're actually assigned a decoding order first. So they're essentially said decode first, but then automatically assign it to be the native. And then this residue is able to actually see the context of the other residues, and so it's able to make a better prediction because it already has those amino acids fixed. So this is really useful for more actual protein design things, because we're not necessarily designing a sequence N to C. We also may have a region that's fixed, and we want that to influence everything else around it. So this is more useful for protein design. This is also highlighting the symmetry and how you can tie positions together. So maybe we're trying to design the C3 symmetric protein. We have 3 chains. We have 2 positions that are already fixed. And we're trying to choose this next one. But we still want it to be symmetric. So we make a prediction, or we compute the probabilities, but we actually average them across all 3 positions so that they're identical. And then we sample that and figure out what is actually going to be put. Questions?
So the decoding order in the ProteinMPNN decoding section, so after you choose your fixed amino acids and have them first in the decoding order, is the rest just randomized?
Yep. And every time you run it, it'll be a different decoding order too.
residues at the interface are important, but they're not on the same chain. How does ProteinMPNN handle that?
So it still looks at them because the nearest neighbors are based on 3D space. It doesn't really care that it's in a different chain. They're still nearest neighbors, so it's still going to be able to talk to them. Okay, the loss that was trained was this categorical cross entropy loss between the predicted sequence and the native sequence. Really, all that means is we have a probability distribution over the different amino acid types. We know what the native is, in this case, glutamic acid. What we want to do is increase the probability of selecting glutamic acid while decreasing the probability of everything else that is wrong. So that's really all this loss function is trying to do. So every position is making a prediction, a distribution of what its amino acids are, and then we're pushing the native one up while decreasing the others. Yeah?
Sorry, maybe I didn't catch it. Can you describe to me more how that probability distribution is being determined?
So after looking at the structure, we have the encoded protein structure. Then we decode a first residue. It looks at its nearest neighbors, gets to decide what it should be, and then it chooses that we sample from this distribution. So really the model, so each residue is looking at its neighbors and then choosing based on what has already been decoded around it or not decoded around it. It makes a prediction of what it should be. It's really just a linear layer after the embeddings.
Is residue, or I should say, residue dependent?
Yes. Yeah, so this would be technically an L by 21 dimensional probability distribution.
Training, you're making sure that the residue that you predict is like the one in the sequence.
Yes.
I guess what I was saying though is if you have a protein, right, at one position, if you took an MSA, that one position might vary considerably. And so if you're trying to minimize the loss between, say, one position and this glutamate, but actually across several domains of life, it varies a lot, then your sequences, you're going to be training the model in such a way that I think it would be more constrained, I think. One
small caveat I think to keep in mind when you're talking about like creating a distribution of acceptable residues based on the evolutionary history, maybe the profile, the PSSM, you are assuming that they all fold into the exact same structure.
Yeah.
So maybe you would actually be better if you had a structural ensemble that you were making a prediction for sequence-wise. So that is one assumption that you are making, but just, yeah, keep in mind. It is a good idea though. Yeah.
Well, one thing that comes to mind too, I think it does make a lot of sense, but for each protein, there might be compensatory mutations. And so if you're predicting a distribution of, say, lysine or aspartic acid here, then this position should either be a negatively charged thing if it's a lysine or positively if it's a aspartic acid. So
yeah,
there would be some dependency on the exact identity here too.
Yeah, so what Ben's talking about is the correlation structure between each residue. If you're doing a PSSM, you're not necessarily capturing that correlation structure. So it'd probably be better if you had an actual joint distribution over every single position at every single time, rather than maybe a marginal.
The loss feels pretty similar to the perplexity of a measurement.
Yes. So when you create this, you transform this into a negative log likelihood, and then you create the do e to the negative log likelihood to get the perplexity. So yes, you can just simple transformation to take this into the perplexity. Yes, good observation. Yeah.
Is there a way to instead limit it to one residue, but kind of similar to what Aiden was saying, but instead like this property of residues, like hydrophobic residues, weigh them more for this position? Is there?
So you can do that in inference time. That is a feature that Hustis has implemented. So you can bias amino acids at specific positions towards specific amino acids. You can bias residues at specific positions towards specific amino acids. Sorry. But yeah, training that may be difficult. But yes, that during inference time, super easy to do.
Just ask.
Yeah, go for it.
I guess my question was like with the biases, I mean, I understand like putting a full bias against something and just completely eliminating something.
Yeah.
That I've tried and it has not looked at the designs. But when you put if in a weak bias, do you think that because the model hasn't been trained on it, that do you have some recommendations for getting a better output when you do put like even a gentle bias on something? Or like, is there a way to kind of compensate for the fact that it has not been trained with?
I don't know how much you need to worry about that because like when you're actually sampling, so the model is still producing its distribution of what it thinks. And then you're just kind of modifying that, adding some extra bias towards specific places, and then it still independently samples that. So like, I don't know how concerned you need to be that the model hasn't been trained about, or trained with that bias in mind. But you can imagine actually giving that bias ahead of time. So if you like randomly sample a bias to be added, you can give that as an input feature to the model and have it learn about how to better select things based on the preferences of the user. You can totally imagine creating something like that actually. That may be useful, I don't know. It'd be maybe a little tricky to set up, but doable. Cool, okay. So the limitations, the first of which has been addressed. The main idea here is that it was trained on the entire PDB. The PDB includes proteins that are embedded in the membrane, which have very different properties than proteins that are solvent exposed. And ProteinMPNN has learned to memorize those kind of structures. In order to do good on the test set, or on its training set, it needs to recognize how membrane proteins look. That's kind of how to do better on the overall training set. So when it starts to recognize them, often like these long alpha helical structures, it'll start to produce hydrophobics that are really popular in the membranes. So one way that to get around this is to use the soluble version of ProteinMPNN. The main difference here was rather than training on the entire PDB, you remove structures of membrane proteins. Now you have only soluble proteins in your training set, and now the model should be more biased towards polar on the outside. The other limitation is accounted for by ligand MPNN, but ProteinMPNN does not account for other biomolecules. So that is just another limitation. Oh, question?
Yeah, is there a feature at all with ProteinMPNN where you can actually try to like allow for the design of disulfide linkages?
Not out of the box. You can imagine modifying it to create something like that. Maybe trying to like, without any, like with everything masked, make a prediction of where it thinks, create the probability distribution for every residue at first, and then maybe select a position to fix to a cysteine that the model thinks would be a good position for a cysteine, and then repredict everything, and then maybe fix something else that is close that may actually form the disulfide. So you would have to hack it a little bit, but yeah, that's possible.